So in the last two lessons, we've learned how to calculate binomial probabilities in a single experiment, and then we've also looked at how we can calculate the mean, variance, and standard deviation when we're looking at a binomial distribution. And that happens when we've got that certain experiment being carried out many, many times, and we want to know the average or the mean of what might happen. But what you might have noticed is that when we have a really large number of trials, the calculations become quite difficult. And in fact, our calculators sometimes can't even cope with them. Now, you've seen this in your assignment that you did, where you had to calculate the probability of getting a certain number of basketball shots in out of 120 shots. The calculators that we use in our classroom weren't actually up to the task, and we needed to use an Excel spreadsheet. And this happens because we end up with really large factorials in there and fractions that have got huge numbers either in the numerator or the denominator. So when we have a large number of trials, the calculations become tedious because they've got such big numbers in them, and we also might have a lot of actual calculations to make. So in this situation, we can use normal distributions to approximate these calculations. Now, it should be specified that this is just going to be an approximation, but the higher the number of trials, the closer that approximation gets to the actual result that we would have got if we'd used the binomial method. So we'll have a look at an example here. We'll have a look at how we would go about doing it with a binomial distribution, see that it's tedious, and we'll approximate the result using the normal distribution. Now, our example says, if we know that 1/3 of voters will vote for a particular party in an election, find the probability that of 10,000 voters in a certain electorate, between 3,300 and 3,400 will vote for that party. Now, if we were doing this the binomial way, we'd need to say, all right, we've got this distribution where 1/3 of the people are going to vote one way. That means that 2/3 are going to vote the other way. And we're polling 10,000 people. So every single time that we find out which way someone's voted, they've either voted for the party or they haven't. That's one branch. So if you imagine a tree diagram, yes or no, and then another person is asked a yes or no. Now we can have the first person voting for them or not, the second person voting for them or not, 10,000 times. So clearly this is a tree diagram we don't want to draw. We've learned an easy way of finding any one term using the binomial method, where we say any one term is going to be 10,000, choose R, 1/3 to the power of R, 2/3 to the power of 10,000 minus R, and we also know that these two numbers need to add to 10,000, and the number here needs to be one of these two, and we found that it's actually a lot more straightforward just to use this number down here. But the problem with this question is that effectively the probability that X is between 3,300 and 3,400, there's a whole heap of work to do, because we need to find the probability that exactly 3,300 people voted this way. Now that would be 10,000, choose 3,300, 1/3 raised to the 3,300, 2/3 raised to the, what's left, 6,700. That's the chance that exactly 3,300 people voted this way. Now we need to add that to the chance that 3,301 people voted this way. So we've got 1/3 raised to the power of 3,301 and 2/3 raised to a number slightly smaller than that, 6,699, plus. There are going to be 100 terms, actually 101 terms in here, because we need everything from here to here. Now, clearly that's a massive amount of work to do. We could get a spreadsheet to do it, but doing it by hand and with our calculator is clearly not really something that we're keen on. So instead of doing any of that calculation, we can say that for any binomial distribution, now remember we specify these with the capital B, and then in brackets we specify the number of trials and the probability of success, because that information is enough to know everything you need to know about a binomial distribution. We can say that this binomial distribution is approximately equal to, not exactly, but approximately equal to, a normal distribution that has a certain mean and a certain variance. Now, why have we specified these two things instead of those two? Well, what we need to know about a normal population to know everything that there is to know about it is its mean and its variance. If we know those two things, then we know how far along the x-axis we need to shift our mean, and we know how spread out the data is, and that gives us everything we need to know to calculate z-scores and probabilities. Now here, we've specified this normal distribution two different ways. Normally, with normal distributions. We call the mean mu, we call the variance sigma squared. But here we've already worked out that the mean of a binomial distribution is NP, where N is the number of trials and P is the probability of success. Now, if we are approximating one distribution based on another, it's going to still have the same mean and the same variance that it would have had, right? So we can use NP to calculate the mean, and we can use NPQ to calculate the variance of this new normal distribution based on what those figures were, the mean and the variance, for the actual binomial distribution. So now carrying on our calculations over on the side here, we can see that for this particular example, N was 10,000 and P was 1/3. So that means that the mean was 10,000 multiplied by 1/3, just doing N times P. So that means we have 3,333 and 1/3. And the variance is going to be 1/3 multiplied by 2/3, so that gives us, what, 2/9, multiplied by our 10,000. And that's going to give us 2,222 and 2/9. Now to calculate z-scores, I'm going to need standard deviation, not variance. So I actually need to find the square root of 2,222 and 2/9, and that would give me, it's roughly 47, let's say roughly equal to 47.14. Now I'm going to save that in my calculator as A. And I can now go ahead and find the z-scores that I need. Now my question is asking me, what is the probability that X is in between 3,300 and 3,400? So now if I'm converting that to z-scores, I'm saying, well, that's the probability of Z being in between whatever this is as a z-score and whatever that is as a z-score. Now remember how to find z-scores? We're basically saying how many standard deviations above the mean is this, or below the mean, or whatever. So let's do this one first. It's clearly below the mean. How far below the mean is it? It's 33 1/3 below the mean. So 33 1/3 divided by my standard deviation, which I've saved as A. Oops, wait a minute. Divided by A. There, tells me that this is a z-score of 0.7 or so. So it's 0.7, but it's below. So I know this is a z-score of negative 0.7. Now just think about whether that makes sense, roughly. It's 33 1/3 below the mean, and 33 1/3, does that seem like 0.7? Yes, and it's below the mean. Whereas our upper score, if we do 3,400 minus 333 1/3, then we get 66 6/7. Now 66 6/7, how many standard deviations does that seem like? 1 and a bit, right? So thinking that through helps you make sense of it. Let's divide that by the standard deviation, and we can see that we get let's call it 1.42. So we've rounded this off to 2 decimal places here. Actually, the last answer I should have probably rounded to 2 decimal places as well. That would be 1.71, both to 2 decimal places. Okay, so now we can use our z-score tables to say, hey, what's the probability that Z is in between this and this? Now, the way that we want to do that, quick sketch, if a z-score of 1.42 is up here, and a z-score of negative 0.71 is down here somewhere, we want the probability of a score being in this zone. I can see that they're just a 1 decimal place, so actually 2 wasn't really necessary there, but the chance of being to the left of 1.4 is 0.9192. So in other words, 0.9192 of the scores are smaller than 1.42. So that's that entire section. So I need to do the probability that Z is less than or equal to 1.4, and then I need to subtract this part out here, which is the section that I don't want. So I'll need to subtract the probability that, now remember you can't look up z-scores for negative numbers, so I'm actually going to do a bit of thinking here and think, all right, well, let's look at positive 0.7. It's here. And if I look up my z-score, the probability of being in this whole section, 0.7, is 0.7580. Now, if there's 0.7580 chance of being to the left of 0.7, can you see how the top tail here, the small part, will be 1 minus that? And that's going to be the exact same size of this tail. So I want to subtract 1 minus the probability of z being less than or equal to 0.7. So that means I need this number, 0.9192, minus 1 minus 0.7580, and I think you'll agree that that is a much easier calculation than what I was proposing doing over here with 101 terms, all of which were really complicated. I've got 0.9192 minus 1 minus 0.758, and I get 0.6772. So let's just think about what that means. If we know that 1/3 of the voters vote for this particular party, and we poll 10,000 people and say, hey, how are you going to vote? We're expecting about 1/3 of them to vote this particular way, because that's the probability. So getting around about 1/3 of them voting that way seems very likely, right? It's pretty likely. So 68% of a chance that that will happen, it feels about right. Now, something to remember is that this is an approximation of the actual score. And you'll notice that I rounded my z-scores to 2 decimal places, but then when I looked up a table that only had 1 decimal place on it, I went ahead and used that. In your book, you've actually got a series of z-score tables there that actually have 2 decimal places in them. So if you'd done this calculation here using a different table that's a little bit more accurate, your answer would be slightly different. But important to remember, this is an approximation anyway. So we wouldn't then give a ridiculous number of decimal places in our answer. We'd say, look, we're looking about 68% chance of this happening. It's going to give us a ballpark answer that's pretty good, and it's going to be closer to the actual result the more trials we're looking at.